talk about greenhouse effect, starting with the description of major greenhouse gases. Learning objectives in this lecture are to refamiliarize yourself with the notion of infrared spectrum, diatomic molecules, and polyatomic molecules. Familiarize yourself with the notion of dipole moment. Familiarize yourself with the definitions of greenhouse gases and greenhouse effects. Familiarize yourself with the black body spectrum of the Earth in the presence of greenhouse gases in the atmosphere. Let's talk about greenhouses. The surface emits 390 watts per meter squared of long-wave radiation, but only 40 watts per meter squared makes it directly out to space. The rest is trapped by greenhouse gases and clouds. A more intuitive way to understand the greenhouse effect is to pay attention to desert weather. In the desert, there are no clouds and little water vapor into the atmosphere. During the day, the climate is similar to the one-layer model, thus it is quite hot. At night, temperatures plunge because there is little greenhouse effect in contrast to non-desert places with greenhouse effect. Our objective in this lecture is to describe how the greenhouse effect affects Earth's temperature. We will start by defining greenhouse gases from the perspective of their effects on Earth's climate. Dry air is composed almost entirely of three gases: 78% nitrogen, 21% oxygen, and 0.9% argon. These gases are important for life on Earth, but have no significant effect on weather and climate change because they are not greenhouse gases. The remaining 0.1% of dry air includes carbon dioxide and methane. Carbon dioxide and methane are important constituents of air, despite the fact that their quantities in the atmosphere are tiny, because they can absorb heat energy radiated by Earth and thus can heat the atmosphere. Other greenhouse gases are water vapor, ozone, nitrous oxide, sulfur hexafluoride, and more. Again, dry air is composed almost entirely of three gases: 78% nitrogen, 21% oxygen, and 0.9% argon. The remaining 1% of dry air is mostly inert gas, or 0.93%, plus a number of other gases. Carbon dioxide is 0.038%, which equals 380 parts per million. And methane is 0.00018%, which equals 1.8 parts per million. These are important constituents of air because they have the ability to absorb heat energy radiated by Earth and thus to heat the atmosphere. Air includes many gases and particles that vary significantly from time to time and from place to place. Important examples include water vapor and tiny solid and liquid particles. Let's talk about ppm, that is, 1 part per million parts. The expression 1 ppm means a given solute exists at a concentration of 1 part per million parts of the solution. Just as percent means out of 100, ppm means out of a million, and ppb means out of a billion. The use of ppm and even ppb is another way of expressing how small the amount of greenhouse gases that we are dealing with in climate model compared to nitrogen and oxygen are. This table shows some characteristics of major greenhouse gases. GHG stands for greenhouse gases. ppb stands for parts per billion. And warming potential stands for the total radioactive effect per molecule over 100 years, relative to that of carbon dioxide. Not all greenhouse gases are equally important. Water vapor is the most important greenhouse gas because there is so much of it. The main source is evaporation from the oceans through the water cycle, as described in the previous lecture. Carbon dioxide is the second most important greenhouse gas. Its current value is 400 parts per million. Carbon dioxide will also be the main problem in the future because it is extremely long-lived in the atmosphere. About 50% of what we emit gets taken quickly up by the ocean or land. Most of the rest stays more than 120 years in the atmosphere. Methane is rare, at 1.8 parts per million in the atmosphere. But per molecule, its warming power is 25 times that of carbon dioxide. The lifetime of methane in the atmosphere is 12 years, significantly shorter than that of carbon dioxide. Nitrous oxide is extremely rare in the atmosphere, at 0.3 parts per million, but its warming power is almost 300 times that of carbon dioxide per molecule. The lifetime of nitrogen in the atmosphere is 114 years. Now we will talk about the definitions of greenhouse gases. How do we know that a gas is a greenhouse gas? To answer this question, let's first recall the notion of diatomic and polyatomic molecules. Molecules that are composed of only two atoms of either the same or different chemical elements are characterized as diatomic. If a diatomic molecule consists of two atoms of the same element, such as hydrogen or H2, or oxygen or O2, then it is said to be homonuclear. Otherwise, if a diatomic molecule consists of two different atoms, such as carbon monoxide or CO, or nitric oxide or NO, the molecule is said to be heteronuclear. Molecules containing more than two atoms are termed polyatomic molecules. For example, carbon dioxide, or CO2, and water, or H2O. Diatomic molecules, such as N2, O2, and more, and monatomic molecules don't interact with long waves. They are not greenhouse gases. Greenhouse gases are all polyatomic, that is, H2O, CO2, CH4, O3, and N2O. They include vibration mode, which is the transition that absorbs the infrared. The absorption tends to be at a single wavelength. So, we can recognize a greenhouse gas based on its atom composition. The basic idea is that the atom distribution of a molecule indicates if some vibration modes of the molecule can perturb the electrical field at certain wavelengths. Such disturbances indicates the light at these wavelengths can absorb the greenhouse gas, which can emit based on the radiation laws. Understanding why greenhouse gases absorb infrared electromagnetic radiation requires the introduction of bond dipoles, molecular vibrations, and molecular dipole moments. A bond dipole is a vector that represents the degree of charge separation in a bond. For example, we can see the bond dipoles of each of the HO bonds in water. We can substitute the bond dipoles with vectors along the x and z axes. The vector sum of all of the bond vectors in a molecule is the molecular dipole moment. Water has a dipole moment. Water has a dipole moment as shown in the previous slide. However, the molecule carbon dioxide has no dipole moment because the two bond dipoles cancel out. In order for a molecule to absorb infrared electromagnetic radiation and to therefore be a greenhouse gas, there must be a change in the dipole moment during at least one of the vibrations of the molecule. If the dipole moment changes during a vibration, then the molecule has an electric field oscillating at the frequency of the vibration. If electromagnetic radiation is at the same frequency or has the same wave number as the molecular vibration, then the two oscillating electric fields can interact and exchange energy. That is, the molecule absorbs the infrared electromagnetic radiation. Note that the asymmetrical stretching and bending and the internal rotation change the dipole moment of a molecule. That is, asymmetrical stretching and bending are infrared active. Symmetrical stretching and bending typically does not change the dipole moment of a molecule. They are not infrared active. All vibrational modes of diatomic molecules are symmetrical. They do not change the dipole moment. Therefore, diatomic molecules do not absorb in the infrared. Let's repeat this. All vibrational modes of diatomic molecules are symmetrical. They do not change the dipole moment. Therefore, diatomic molecules do not absorb in the infrared, and they are not molecules of greenhouse gases. Nitrogen and oxygen do not absorb infrared because their vibrations produce zero dipole moment. Molecules such as water and carbon dioxide do absorb in the infrared because they include vibrational modes with non-zero dipole moments. Some vibrations, such as asymmetric stretching and bending modes of carbon dioxide, produce a change in the dipole moment and therefore absorb infrared light. However, some vibrations, such as symmetric stretching of carbon dioxide, do not produce a change in the dipole moment and do not absorb infrared light. So carbon dioxide does not have a molecular dipole in its resting state. However, some carbon dioxide vibrations produce a structure with a molecular dipole. Because of these vibrations, carbon dioxide strongly absorbs infrared light. Here are vibration modes of a nonlinear 3-atom molecule of water. Notice that infrared lights can be absorbed only when vibrations produce the dipole moment changes. So, in summary, the making of the greenhouse effect at a given light wavelength is that the wavelength of the vibration of the molecule must be equal to the wavelength of the light. And one or more vibrational modes of the molecule of greenhouse gases must have a dipole moment that disturbs the electrical field. Polyatomic molecules, such as water and carbon dioxide, do absorb in the infrared because they include vibrational modes with non-zero dipole moments. Let's talk about the climate model with greenhouse gases. One question that follows from our discussion in the previous section concerns the effect of carbon dioxide and other greenhouse gases on ground temperature. It turns out that, to a certain extent, we can use the one-layer model described in the previous section to answer this question. The parameter of the climate model most affected by greenhouse gas is the absorptivity and emissivity of the atmosphere. The higher the concentration of carbon dioxide in the atmosphere, the bigger emissivity will be, because the atmosphere will be more efficient at absorbing and emitting long-wave radiation. That is why greenhouse gases have a general warming effect, as shown in the following picture. The energy budget equations at the atmosphere and at the ground can be described as follows. When emissivity is 1, these energy budget equations become those of a climate model with an opaque atmosphere, as described in the previous lecture. When these equations are solved for the two temperatures, we obtain the following. So when emissivity equals 0, these equations reduce to those of the climate model without atmosphere. When emissivity equals 1, these equations reduce to those of the climate model with an opaque atmosphere. Because of the greenhouse effect, we have emissivity is greater than 0 and smaller than 1, which means that the actual effective ground temperature for a given emissivity is greater than the temperature of the Earth without the atmosphere. That is, greater than 255 degrees Kelvin, and smaller than the temperature of the Earth with an opaque atmosphere. That is, smaller than 300 degrees Kelvin. Basically, with appropriate values of emissivity, we can reconstruct average temperatures that are quite close to actual average temperatures, which is 289 degrees Kelvin for the Earth, as shown in the following table. Note that the temperature of the atmosphere is always smaller than the ground temperature. The atmosphere is always cooler than the ground on average. Now let's talk about blackbody spectrum and the Earth. Inspection of high-resolution spectroscopic data reveals that the absorption bands for the 320 through 380 inverse centimeters is caused by water vapor. Inspection of high-resolution spectroscopic data reveals that the absorption bands for the 680 through 740 inverse centimeters region is caused by carbon dioxide. Here is the absorption spectra for water, carbon dioxide, and methane. Notice that even if the atmosphere is saturated with water vapor, a great deal of infrared still gets through. Carbon dioxide and methane absorb the infrared wavelengths that water does not. This figure shows an example of an infrared spectrum. Clearly, in certain portions of the infrared spectrum, radiation is trapped by various gases in the atmosphere. Among these gases, carbon dioxide, water vapor, and the ozone are the most important absorbers. Carbon dioxide absorbs infrared radiation significantly, from about 600 to 800 inverse of centimeters, which also corresponds to the maximum intensity of the Planck function. Water vapor absorbs thermal infrared from about 1,200 to 2,000 inverse of centimeters, and in the band below 500 inverse of centimeters. Except for the ozone, which has an absorption band about 1,040 inverse of centimeters, the atmosphere is relatively transparent, from 800 to 1,200 inverse of centimeters. This region is referred to as the atmospheric window. Carbon dioxide also has an absorption band in the shorter wavelength of the 4.3 microns region, or 2,325 inverse of centimeters. The global distribution of carbon dioxide is fairly uniform, although there have been observational evidences indicating a continuous global increase over the past century because of the increased combustion of fossil fuels. Unlike carbon dioxide, however, water vapor and ozone are highly variable with respect to both time and the geographical location. These variations are vital to the radiation budget of the Earth atmosphere system and to long-term climatic changes. Let's conclude by talking about the budget equations of Kiel and Trimberg's model. This is an illustration of the Kiel-Trimberg energy budget for the Earth in 1997. This represents a viewpoint of the physics that is used to justify the catastrophic man-made global warming hypothesis. At the top of the atmosphere, you have incoming radiation from the sun minus reflected radiation by the Earth equals outgoing radiation emitted by the Earth. At the Earth's surface, you have incoming radiation from the sun plus infrared back into space through greenhouse effects minus thermal and evapotranspirations equals outgoing radiation emitted by the Earth. In the atmosphere, you have incoming radiation from the sun plus infrared back into space through greenhouse effects plus thermal and evapotranspiration equals outgoing radiation emitted to space plus outgoing radiation emitted to the Earth. Here are some take-home points. About 30% of solar radiation is reflected back to space. That is albedo. Out of this 30%, 20% is reflected by clouds, 5% by atmosphere, and 5% by the ground surface. Greenhouse effect makes it very hard for Earth's radiation to escape from space. Greenhouse effect sends back radiation, or long wave down at the surface from the greenhouse effect to the Earth's surface. In other words, greenhouse effects cause the planet to be warmer. Now it's time to take a quiz. Below is the following Earth energy balance equation with the effective emissivity E. Select this factor to obtain an average Earth temperature of 289 degrees Kelvin, or 16 degrees Celsius. Our next question is to demonstrate that the atmosphere in the two-layer model simulates the greenhouse effects. In our next question, consider the two-layer model described earlier for the case in which the atmosphere absorbs the sunlight, or the so-called nuclear winter. Predict the temperatures of the ground and of the atmosphere. Our next question is which one of the following substances are good black bodies? Your options are oxygen, cloud, hydrogen, and methane. Below is the following Earth energy balance equation with the effective emissivity E. Select this factor to obtain an average Earth temperature of 289 degrees Kelvin, or 16 degrees Celsius. Your answer is here. Demonstrate that the atmosphere in the two-layer model simulates the greenhouse effects. The incoming shortwave radiation is transmitted by the atmosphere, just like greenhouse gases. This atmosphere absorbs long-wave radiation energy and re-emits energy, just like greenhouse gas, back to the ground. Consider the two-layer model described earlier for the case in which the atmosphere absorbs all the sunlight, or the so-called nuclear winter. Predict the temperatures of the ground and of the atmosphere. Nuclear winter, also known as atomic winter, is a hypothetical climatic effect. Suppose that some kind of catastrophe injected a layer of black soot into the upper atmosphere. The soot layer is perfectly absorbing both in the infrared and the solar parts of the spectrum. The soot layer is so high up that it is essentially thermally isolated from the ground. Approximate the atmosphere as an infrared absorbing, solar transparent black body. What is the effect of the soot layer on the surface temperature? The energy balance for the atmosphere is as follows. Which ones of these substances are good black bodies? Your options are oxygen, cloud, hydrogen, and methane. The answer is cloud. Remember, there is a large selection of iMode education lectures, which can further enhance your knowledge of earthquakes, volcanoes, climate, and energy. Thank you for listening to this iMode education lecture.